As I said, this part of the lecture, I will talk more about the experiments. However, the first few slides will be still on our trapped particles. And as, oh, it's going fast. So I just recap quickly. We had this slide on yesterday. Thanks a lot. We had this slide on yesterday about the experimental setup, which I explained where we trap the particle, and then I already have shown you some of the data in this setup, including the optical spring. And for completeness, I will kind of finish up the main results that we had there. So from the optical spring, one can infer how strong the optomechanical coupling is, which is here, right? This is essentially alpha G naught, independence of the ratio of the of the power of the two beams, which you saw here, right? There's two beams going into the cavity with different powers, and the ratio is mu. And if we increase the ratio by going to a stronger cooling beam, then the interaction with the cooling beam gets stronger, of course, and we start to cool the system. And that was very nice for us because it was really the first time one could show something like this, dielectric cooled in a cavity, but then also not, because of course we wanted to go to very low temperatures, and all we could do at the time was go to like 50 Kelvin, which is pretty high, and this was because of the high pressure that was still in the chamber of roughly a millibar. Now the damping of the particles is linear in pressure, so one can immediately deduce that at a pressure of 10 to the minus 7 millibar, we would, with the same cooling rate, and if we don't make any other technical problems, be cooling into the ground state. Because the cavity in this experiment was already side-fed. So the good news about this was that one just has to solve this problem with the pressure. I will probably say a few more words on this on Monday, but the thing was that for a reason that is still not known today, particles get lost out of many of these optical traps when one crosses a certain pressure regime. Now, I should not write any more limitation currently, because in this new setup that I showed you yesterday as well, where we have this optical tweezer, we can, like several other groups, go to much lower pressures. One of the groups is like Hendrik's group with Jamie. So this seems to be a solved problem. One just has to combine this tweezer approach with the cavity, which we are doing right now. As I said, so there's many experiments also who have actually shown cooling in a cavity, or at least a signal from a cavity particle. So that's Markus Arndt group in Vienna, a group at ICFO by Ramanujan and Lukas Novotny, and also in this kind of hybrid approach with an electrical trap in Peter Barker's group at UCL. All of these other setups are at low pressures, but are facing one or the other problem when it comes to ground state cooling. Back to our setup, and this is something that should be pretty clear after the things I explained now. So when we want to do quantum stuff with our particle, then I said the cooperativity needs to be larger than 1. And now there's a little difference when it comes to the nanoparticles compared to clamped cantilevers, because at some point this heating rate here is not anymore just a thermal heating rate, but it's due to recoil from photons. So there's photons scattered off the particle, and they go everywhere, and that happens randomly, and this gives kind of another Brownian force noise contribution, which would be this gamma recoil here. And so when we look at the cooperativities of the particles for the case when the pressure is essentially low enough to be neglected, or say we neglect gas damping at all, then this would be the cooperativity expected in exactly the same experiment. of a cooperativity of 5, and one would not expect here a particle dependence. Now, why not? Right? It's something that we do expect. We do expect that the coupling changes with the particle size, but then this goes with the volume of the particle, and the recoil heating goes with the volume of the particle as well, so they just cancel. Which means that you don't win in cooperativity by going to a larger particle, but at some point you will lose because the approximation of a particle much smaller than the wavelength is not true anymore. And here me scattering actually starts to play a role. So on this side, when would we be limited by this recoil scattering? I said a number before already, but so this curve shows the sphere radius and the pressure, and then a line where certain conditions are met. So when the recoil scattering rate becomes larger than the thermal rate, or others said differently, the thermal heating becomes smaller than the recoil, then this is in the blue area. And when the cooling rate is larger than the thermal heating rate, then that would be in the red area. And if we look at our size of particle of roughly 130 nanometers here, then we would be in the blue region at roughly 10 to the minus 6 millibar. So there, pumping down further would actually not really help much for the cooling. I said 10 to the minus 7 on the slide before, and the reason for that is that these things are calculated for an idealized position of the particle in the cavity, which we now, as I showed you yesterday, should be able to do with the tweezer, while the measurement before was for the random particle position we actually had. Yes? Yeah? I'm actually very glad you're asking. This is as funny as it sounds. It's exactly the problem that we had in going to the tweezer approach. No, right? Well, cutting the mirrors is one thing, but the thing is that we can only trap in the mirror when this concentration of particles in the liquid would be at roughly a 10 to the minus 4 mass concentration if we want to trap in the tweezer. But if we do that with the cavity is, as you suggest, completely getting dirty. So we go to, for the loading in the cavity, we went to a 10 to the minus 7 mass concentration. So there's so little particles inside that we can keep the finesse up. Actually, from time to time, one has to clean the mirrors, but that's like half a year's game. So how to solve the problem now with the tweezer? We had, which I maybe say something later about, we had this fancy approach of using a hollow core fiber to transport the particles into the chamber, but then this was technically a bit challenging, and now we do the very low-tech approach. We trap a particle in the tweezer when the cavity is not in the vacuum chamber, and then while the particle is trapped, we put the cavity in the vacuum chamber, align it, and pump down. So this is it was actually a nice day when David came and he said, you know, I had that particle trapped, and then I put the cavity in, and I took it out again, and I put it in again, and I took it out again, and the particle was still there, so we can do that. So, yeah, it's not a very sustainable approach, I think. If we ever want to have higher rates of doing experiments with many particles, then we should better come up with a better solution. But for now, for doing this, it works. I mean, once the particle is there with the feedback cooling, we can keep it for days. So, like in all the other experiments, the trap depths are really high. Okay, good. So much for the particles. Now to something completely different. I was about to talk about what you heard just in the end of the lecture this morning. So I just skipped this. It's That's about the standard quantum limit. I just want to make a remark. In addition to what we heard, when the whole experiment, here you see it, when the whole experiment is done in a cavity, then you still have this phase readout from the photons that are reflected from the cavity when the mirror moves. And this is the phase response of the cavity. And we would detect this reflected light by some homodyne detection. And now the question is, how does this picture of reading out the phase change if you use a cavity in comparison to when we don't? The fundamental limit stays the same, but we get an enhancement on the precision of the readout by finesse over pi. And so if one takes all the numbers, then we come to something. So this is taken from this review where it's very nicely explained and very brief, so it's worth reading. So where the imprecision noise from the measurement can be calculated in dependence of these optical parameters we discussed. And what we find is that it goes with kappa over, and this big G here is the omega over dx. So what we have written there is that this imprecision is proportional to something like something like kappa over G squared, or G naught square alpha square. Now this is something you saw yesterday, right? It's just 1 over this cooling rate that we have in such a system, or Rabi rate if you want. And then there's another term contributing, that's this one. Looks very similar to this sideband pooling term that we looked at. And that's also fairly easy to understand, because when the frequencies get appreciably high compared to the cavity line width, then suddenly the slope of this phase response gets worse because of the filtering effect the cavity has on the light. And that is why we lose in readout sensitivity when the frequencies get very high. So one gets this correction term on the imprecision of the measurement. And then this is just a collection of equations which you saw today already, and here the same one as you saw, but with a factor of 4 here, because it's symmetrized power spectral densities. And what you get then is in your power spectrum, when this is just the intrinsic noise, you get an increase in the power spectrum due to the imposition, and then you drive the mechanical system via back action. And this is the plot one usually sees. The imposition noise, when the power goes up, goes down. Back action noise goes up, and somewhere in between is a sweet spot. And it's important for what I show you next that often there's thermal noise, and if there's thermal noise, then this could be, say, around here. It's flat, right? It's power independent, and then this thermal noise would essentially not make this region here visible. So it has been actually pretty recent that this radiation pressure noise has been seen in an optomechanical system. It's not so easy because you need high powers and high coupling without essentially heating up the system too much. So this is Cindy Riegel's group. And they're actually in a cold atom-based system, but a very optomechanics configuration. This has been shown in 2008 already. Now here with a membrane, it's like 2013. The membrane in the middle approach, this membrane is sitting in this Fabry-Perot cavity. The effect of the membrane is not much different than the one from the particle. And here's a signal and a meter beam, and the signal beam would be driving the cavity more and more strongly, and the meter beam is just used to read out the particle, the membrane motion. And now this plot looks a little bit different than what you saw before. This is the right part of what you have here, the back action noise. And the plot actually starts here in the middle. And then, as I said, there's thermal noise covering. So the brown line is the thermal noise. And when they increase the power, so this is the number of photons in the signal beam, then they see this enhancement due to the back action. So this experiment showed, I think, for this type of systems for the first time, the effect of the shot noise onto the mechanical system. And yeah, but one should keep in mind that they cannot reach this SQL limit because of thermal noise. Now, even more recently, there has been a very similar or very related experiments with nanoparticles. So this is for a nanoparticle that is trapped in an optical tweezer in the group at ICFO, Ramanujan's group. And this is actually always a collaboration between ETH and ICFO, Ramanujan and Lucas Novotny. So what they did is they trapped this particle. They have done many nice experiments on this. And now they can go down to like 10 to the minus 8 millibar. And at this pressure, the recoil heating of the particle takes over. And one can actually understand that as a very similar thing to the back action. And one would also get here this kind of imprecision noise when the laser is too weak, and then a back action noise when the laser is strong enough for the trapping. Everything is a tiny bit different. First, with this particle scattering light out of the system and the limited numerical aperture that one has to collect the light in the tweezer, the detection efficiency of the light is much worse. So one is actually very limited in this kind of measurement by simply bad detection efficiency. I mean, in the Optomechanics, yes? I think they calculate an overall efficiency, including the scattering into free space and every component, and so of 5 times 10 to the minus 3 or so, or 4. Yeah. While in the other experiment, essentially everything. I mean, compared to that, essentially everything. But still, this is can be understood as effect of back action if one thinks about the particle as a kind of a beam splitter scattering into all the 3 modes, and then one looks at the noise on this contribution, right? And one can actually see this heating directly when one cools down with feedback cooling. So in this case, so Hendrik mentioned it, I think. So one can do feedback cooling on these particles, and in this case, they go down to 60 phonons. And so it's roughly, I didn't calculate it, but on the order of millikelvins or sub-millikelvin, quite sub-millikelvin. And then one can look at the reheating rate, and they did that for different powers and different particles, and it's all pretty consistent with what one would expect for recoil heating. It's of course not so easy if you really want to very well exclude all the other sources of heating, right? Then you would, for example, have to take care that you know exactly what the position noise in your experiment is. That is in this case not excluded experimentally, but by comparison to the calculated numbers, one sees that this is consistent with what one would expect for recoil. Now, a little remark still that is related to this experiment, and that I am actually not very aware of for a very long time by now. Now, with these particles, right, we were talking about Q factors, and the Q factors increase when we go down in pressure, and at very, very low pressures, we can get incredibly high Q. Then we know that there's this recoil heating, but the recoil heating is something like a momentum diffusion process. So it would heat the particle, it would decohere the particle, but it was not so clear to me, and I just believe I'm the only one, that it's that the Q is actually also getting limited by this recoil process. And the reason, I mean, this doesn't have to be like this, right? For recoil scattering, I don't need to assume that the fluctuation dissipation theorem holds. I could just have a momentum diffusion until infinity without any damping. But what actually happens, and it's also described in the paper, it's not something I invented, of course, is that this recoil heating happens in all kinds of directions. And if the particle moves in one of the directions, then you would get a Doppler shift of the recoil light. Right? And this Doppler shift, if one calculates it, is just h bar k in the k some upshifted k in the one direction, and then the momentum kick in the other direction would be h bar and the downshifted k. Right? And this is the delta p per photon that one gets on average for every scattered photon in a certain direction. Right? And from this one can easily calculate. So this would be h bar k plus some delta k minus k plus some delta k, and this is equal to h bar k times 2 h bar k times delta k over k. Right? And then the Doppler shift is like delta k over k is approximately delta omega, delta nu frequency of the photon over nu, and that is velocity of the particle over c. And then we see here that this is 2 h bar k times velocity over c. Right? And that shows that we have a velocity-dependent shift, a velocity-dependent momentum kick on the particle, and then this multiplied by the number of particles gives you friction ton. And the final temperature that one achieves, if one would equilibrate to that, is h bar omega. Omega naught I wrote here, I usually write omega cavity. So this is corresponds to the energy of a photon. And that's roughly 10,000 Kelvin. It's independent, it's interestingly independent of the particle and the laser power. It's all independent. Okay. And these experiments have been mentioned this morning. I just wanted to point them out. So there's ideas on how one can resolve better than the ground state extension, and it's only very recent that one really achieved also a squeezing of a mechanical resonator with exactly the scheme that you heard this morning, right? In this micro-mechanical resonators driven by microwaves. There's several other ideas how to do sort of Q&D measurements, and next thing I want to do is to present one of them, which is born in the Aspelmeyer group. That's pulsed optomechanics. So pulsed optomechanics is when I first heard about optomechanics, and I was talking to Markus Aspelmeyer, then this was the kind of thing I thought of. Right? You shoot a very short pulse on some resonator, and then you look, for example, at the phase readout or so. For me, this was rather the first intuition on how you would do it, instead of using all this continuous light fields and fiddling around with all this continuous degrees of freedom and spectra, which I didn't know at the time. So that was something that Michael Renner actually looked into already in Markus's group, and this is the scheme. So we have some cantilever, and there's, as usual, a light field coming, but in this case, the interaction of the light with the cantilever would be much shorter than the period of the mechanical resonator oscillation. And the idea behind this is that one can actually do a type of Q&D measurement with this. So one can measure the position quadrature, so essentially the position of the of the mirror with a strong pulse. And if one starts off with this is a phase space picture. If one starts off with a thermal state, like occupation of 10 or so, and then I do a measurement on this system to read out the position, then I learn something about the position, and I can describe my state in phase space with a better precision. What I didn't learn about is the momentum quadrature. So this stays the same with essentially. Now, I just have to wait for a quarter period until my mechanical oscillator exchanged X and P essentially. And then this is a rotation in phase space here that just happens by the normal oscillator dynamics. And then I can do such a measurement again. And with the second measurement, I would again confine the state. So all I did is with these two pulses, I read the position and momentum of my mechanical oscillator using the fact that it's high quality. And I learned about this position and the way this was phrased, and one can discuss what it means exactly, but the way this was phrased is cooling by measurement. Now, I didn't really cool the oscillator in the sense that it lost energy, right? On average, it doesn't lose energy at all. In fact, I say this in a moment, it wins energy. But then on the other side, if I mean with temperature that my state is a highly unpure state that is very distributed very far in phase space, and all I need for my further experiments would be a purer state, then I could say this is a colder or purer state because I have made some confinement here in phase space. Now, the stronger I make this measurement, the more photons come, the better I can read out the phase. You heard about this argument this morning also. But now with this very short pulse where I essentially read only the position at a certain point in time, I could, for an arbitrarily large number of photons, I could read the precision arbitrarily well below the 0-point fluctuations. And in order to conserve the uncertainty relation, I would have to get this, this extension in the momentum quadrature. And this is, again, simply this argument from this morning. The shot noise is giving me this, right? The shot noise will just increase the momentum distribution of the oscillator. So the question is, what do you need to do in order to get such a strong measurement that you would do this, would get this squeezed state where you're below 0-point fluctuations in position and then accordingly squeezed. And there's some measurement parameter introduced for that. I don't go into how one would calculate that, but let me tell you a bit more about what one can do with this. So, as I said, one can prepare a squeezed state with essentially a single pulse if you just measure precisely enough. One can prepare a pure, yeah? Yes? Sorry? Yes, so we are using the XX interaction, so in that sense it's a QND pulse. And that's where, yeah, that's where the difference is to the other scheme. So the whole approximations don't work anymore for this short pulse scheme. So the idea is, say we start off in the ground state, and the extension here would be just x 0-point fluctuations. And now I do a measurement of the position, and I find my state here, but my precision of the measurement is just like this, right? Then what needs to happen to fulfill uncertainty, and what also happens because of radiation pressure shot noise, one can show that the pulse needs to be so strong that the shot noise on the pulse would give me a larger extension in P. And that's single shot, and that would be squeezing. And one can achieve that only with sufficiently high measurement strength. Exactly. Yes. And it's also probabilistic what exactly the squeeze state would be. And the other thing one can do actually is state tomography. Now, yeah, sure. Mm-hmm. Exactly, yes. Exactly. Yeah, 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 exactly. And actually, it's actually, I realize that it's not so clever to explain both on the same picture, because if I want to, if I want to prepare a pure state, then what I would do is do my measurement strength such that I, like a ground state size, a coherent state, then I would measure just the 0-point fluctuation size, and then again on this. Yes. Mm-hmm. Yes. Yes. Yeah. So if the measurements that one did here were really sub 0-point fluctuation, then I would have to elongate the state here really again. So yeah. So I can essentially prepare all kinds of Gaussian states, but if I want to have it coherent, I would need the right measurement twice. And that in the end it means that I measure with these two measurements, I measure at the SQL, and then I know kind of what state I had, so to say, initially as a coherence. I mean, in the end, if one did optimal estimation of the trajectory on the SQL limited, then one would all the time, conditioned on the measurement outcome, also have such a state. Um, I, I don't know. No, I, this, I think. Yeah, right. Exactly, yeah. We just rely on the dynamics. Yeah. That's very related to what Andrea said about this. I think about this that one almost always couples to the position quadrature. I think a rotation would require to do a so the back action would tell me something about the light actually, not about the mechanical resonator. Yeah, but yeah, I need to think about that. I know that we thought at the time, oh, can't we do at the same time a measurement of P? And we didn't have any idea. But maybe there's an idea. We can talk about it. Yeah, let's talk about this then. State tomography. So say I don't have such a nice round thermal state, but I have just something in space, right? This would be something. And now I know, now I want to know what my state actually is. It could also be a cat, but let's just say it's something fun. Then what I can do in my measurement, I cannot just read this out, right? Because these two don't commute. I can't measure them at the same time. But if I repeat my measurement many times with the same state prepared, then I can do a projective measurement on my position, and I would see kind of a projection of this momentum, of this probability distribution here. And in the same way as before, if I wait a little bit, then my state rotates, right? And I see it a little bit under a different angle. And if I, for many angles, do this kind of projective measurement, then out of all these pictures I get, I can tomographically reconstruct the initial shape here. So that would be a way, if one had a means to prepare some funny mechanical state, to read it out. Yes? Yes. That's the issue. Then at the same time, if I have a dynamics that I mean, if my coupling to the environment is so small that I say after a rotation, I still have essentially the same state, then it's fine, right? And so a Q of 10 to the 8 means in the end that I can do 10 to the 8 rotations. So in that sense, the approximation is pretty good. But I agree, in the end, it's not exactly the same state. Yes. Yeah. So actually, yeah. So this point here comes, so to say, after that, right? I didn't say how I prepare the state initially, so I have no clue how we would prepare, say, more interesting state. In fact, one can, of course, classically just to play around do that, and this is actually what I show now. So a very simple setup. These are cantilevers with a, sorry, yes, these are cantilevers with a pretty low frequency of 1 kilohertz. They're very long, a few millimeters, and they are mounted in vacuum. So the mechanical quality is also not terribly good, but it's like 3 times 10 to the 4. And one just uses a laser that is amplitude modulated to shoot a strong pulse on it. And we also, I mean, I say we out of habit, but it's not my experiment, right? I should point it out. It was I was actually not involved in that. So it's reflected, and then together with a local oscillator, we can measure again the phase of the light field. And now, if this whole thing is in a thermal state initially, and we do a measurement, then at different times doesn't really make sense because we only do a single measurement. So we just wait for a while and look at the state because it's symmetric. It will always look the same. This is a probability distribution. One can reconstruct the state, and this would be the phase-space distribution of this state. So far, so good. The thing is at 1100 Kelvin because with this kind of setup, at 300 Kelvin, it was not so easy to show something very meaningful. So the whole system was driven with the piezo, still shaken and then a little bit hotter, so to say. Now, if one applies a second pulse, as I described, one does this projection here, and it gets narrower in one quadrature in phase space. And if one does the second measurement, one can make it narrower in the second direction. I should point out again, of course, we are not even close to some 0.5 dimensions. Just a proof of principle. Now, after that, we would have an equivalent temperature of 16 Kelvin for the whole system. Or one could actually drive the state, and then by driving the state, we can, with this piezo on the resonance frequency, we can look at the tomography of this again, and the probability distributions we get look like this, and a reconstructed phase-space picture would be that, right? Looks, if it was around the 0 point, it would look like a Fock state, but it's far from being anything like that. Sorry? This specific shape. So the oscillator is driven coherently. It's not a noise drive, right? So it's actually getting in phase with the drive, and it would be kind of a thermal state that is slushing around in the, and that's why there's no occupation in X equals 0. It's an excited state. So in this picture here, if one looks at so if one does this driving, one would get a state that is kind of, so look at a coherent state, and that you would have initially, and then you drive it, then this is making a displacement in phase space. And now with the thermal, starting with the thermal state, this is kind of randomly displaced in all directions. And then it doesn't heat up more because there's damping from it. Now, of course, the idea is that one doesn't stick to this demonstration setup, but that one actually goes to a real measurement strength where one can see squeezing. And this is an optomechanical structure that can do that. Again, we are with photonic crystals because photonic crystals have such a high photon-phonon coupling. And so here you see these two bars. It's a little bit of a different structure that spread and get closer together, and that modulates the cavity length, so to say. It works at 1550 nanometers. And it has a pretty high line width of 2 gigahertz, but in this case, this is a good thing. I didn't say that before. We always, with the continuous schemes, we always wanted to have sideband resolution, narrow line width of the cavity. But here, the whole scheme wouldn't work with a narrow line width, because in a narrow cavity, I cannot send a short pulse. So we need a wide line width cavity. And then the thing has also a very low frequency. This is why we have this other geometry here of just a megahertz. And that would give this value of chi larger than 1. Oh, I actually don't have that here. The reason why we didn't do it, Ralf Rieding is actually the head of this project. Why he didn't do it yet is because this structure here, as many of the other structures you saw, has a terrible set of modes in there. And now this is a downside of this pulse scheme, because if I just have one single mode, I can nicely, you know, as we talked, wait for the rotation. But now if I have all these kind of modes and all of them affect my light field, then I don't actually know exactly what I read out, because I don't only see this one mode that I projected, but there's all the other modes which do what they want. So one solution out of this problem would be to do monitoring with a weak beam of all the modes that would be like 6 or 7 close to the other frequency. And then all these modes one would actually have to monitor, and one can use optimal filtering for that in order to really separate this one mode out. It's terribly cumbersome. Another thing that would be nice, but it's not clear how you would actually experimentally realize it such that you get such a high coupling, would be nanoparticles, right? I showed you that nanoparticles have essentially just 3 modes, and we would be very well able to separate. The other problem that one gets if one would do it with nanoparticles shows that we were putting something under the carpet. And I come back to this a little later because it's actually useful. So when we have this short pulse, we get this measurement of the phase, and we get this radiation pressure shot noise. What we didn't talk about so far is the whole photons are being back reflected, and each of them makes a momentum h bar k, right? It's not just the noise that is there. So there's actually a classical displacement according to n times h bar k on the system. With a clamped resonator, it just means that I have it terribly far out in my space. It doesn't get less pure because I do this. It's just this displacement. But with a nanoparticle, I might just kick it out of the cavity, for example. So one would have to come up with a scheme where one doesn't do that, where one can do this kind of measurement without the kick. It's just a power enhancement. Yeah, just for the power enhancement. Well, in a sense, when this high parameter goes beyond 1, then the back action should be become visible. Yeah. So in this measurement, and one would see it here mainly because of the incredibly large which number I didn't. Oh, here it is. It's a very large single photon. Right? When we were talking about that before in the old pictures or so, you saw something on the order of up to 100 hertz or so, except for the photonic crystals. And here we're talking about 0.5 megahertz, single photon. Okay, so that's great. Once more, sorry. Um, to my, so I don't know the system well enough because I didn't work with it myself, but to my knowledge, there's nothing. To my knowledge, there's really just a dispersive and not a dissipative effect on the Okay, so this was still a kind of classical experiment, and where it should go, I will talk a little bit later about a scheme where one can maybe, hopefully, in the middle future, use that for something at the interface of quantum gravity. But what I want to start off now is just using, again, we go back to the continuous driving systems and just using the tricks that we talked about in the first sections. And before that, I want to come to one of the older ideas that I don't know, maybe did that come up last week sometime? No? So that's a fairly old proposal that I think is quite well known, at least in some part of the community, where there was a very, let's say, simple-minded, but one actually maybe also feasible in the far future idea on how one could get a superposition state of macroscopic mirror. And the idea was one just uses a single photon source and a beam splitter, and then we get a superposition state of the photon between A and B arms, right? And then there's two equivalent cavities. One of them is not having a micromechanical mirror inside, and the other one has this tiny mirror. And depending on where the photon goes, it kicks the mirror or not, right? So after the photon interacted with the systems, we have kind of an entanglement between the photon position and the mirror whether it oscillates. And now this is put back onto the beam splitter and detected here. And we come back to what Hendrik also mentioned today already. One needs to erase now the information that the photon carries about the mirror, and this is done here in this detection, and this only happens at certain times. So whenever the time just corresponds to the period of the mechanical oscillator, actually I believe it should be 2 pi over omega m, it's out of the paper, or they have a different definition of omega m. Then there's no way to know from the phase of this interference, there's no way to know whether the photon was actually going into the one or the other cavity. So we would see a visibility in the a high visibility because the mirror has no information stored about the photon for these times in the interferometer, and then the visibility would go down for times when the mirror actually could be telling us something, whether the photon hit it or not. Now they went through all the numbers and actually have been or are still, I don't know, working hard to realize this thing. At the time, they took typical optomechanical parameters that were around in 2003 and estimated that the ratio of Q over T, I showed you that this is a relevant ratio, that the ratio of Q over T needs to be improved by 6 orders of magnitude from the values discussed in this letter, which corresponds to a Q of 10 to the 5 and a T of 2 millikelvin. Now, from probably all you heard by now, at this stage in time, we cannot do that yet, right? Because even if the Q is 10 to the 8 now, we would still need 2 microkelvin as the temperature of the environment, not like, because this relates really to the decoherence rate and not to the temperature of the mechanical mirror itself. And this was particularly devised, I think, together with Roger Penrose, also for testing Penrose. Now, we go to, as I said, to these nice interactions we have, and let's ask whether we can do such a kind of entanglement in the way that we see optomechanics today. And this has been proposed by someone else. Also, I mean, there have been many proposals how to do entanglement, and the particular one I propose is from Sebastian Hofer, who is working partially in our group and partially in the group of Clemens Hammerer as a theorist. And it's essentially just picking up this idea of the squeezing interaction. Can we do a two-mode squeezing interaction with our optomechanical system? Because what we would expect is an EPR entanglement between the mirror and the light field after that. And this type of EPR entanglement could be demonstrated if we look at the quadrature of the light and the quadrature of the mirror. Here the difference, and here the sum of the momenta. And the variance of these values should, for an EPR entangled state, be 0. And this proposal is then using a pulse again, but this time the pulse is much longer than the period of the mechanical oscillator, so that we can really think in terms of these sidebands that we've been talking about. Also needs to be a sideband resolved cavity. There's a blue detuned pulse coming. It's driving the system parametrically, so to say. It comes back out. And then I can use a second pulse, red detuned, that uses my beam splitter interaction to read out the state of the mirror, right? I somehow need to prove my entanglement. And the way it is actually drawn here is already going one step further. Namely, if I do a projective measurement on the system, like this is often done in continuous variable quantum optics, or also when reading out like atomic ensemble systems, then I can use some other pulse where I write some quantum state on. I make a joint projective measurement on the two, and this would, because of the entanglement, result in essentially teleporting this state onto the mirror. Now, this is not really the teleportation. What you would still need to do is, according to the measurement outcome, one would still do a shift to the mirror. This is something we can't do experimentally right now. But in principle, this is an idea to teleport a state from here onto the mirror and then read it out with the red pulse. And this is an experiment that, like without the teleportation bar, just the entanglement, that has actually been done again with this microwave drum systems. That was in Konrad Lehnert's group. And so what they did, they used this kind of system. They can send in some microwave beams. It's the two modes the red and the blue pulse I was talking about. Here you have this LC circuit you saw this morning, and one can also connect it to some thermal source, which is just there to calibrate the detection. There comes the cooling pulse, so one cools the system to the ground state. This is something they can do. Then one comes with the blue detuned pulse, which would amplify the whole system. So this is where the mechanical, this is when you look at the quadrature of the readout of the blue pulse when it's back reflected. So it gets up here because you occupy it. We have this A dagger, B dagger thing, right? And at the same time, the mechanical structure should be occupied. And then one can wait for a little bit. So this entangled state is so to say stored. This part of the mechanical part of the entangled state stored in the mechanics for, in their case now, 10 microseconds. And then one comes with this red pulse, and that is just reading out the mechanics, which is indeed also highly exciting. And then if one looks in phase space for different powers of this pulse, then one would see that that in this phase space for small powers, there's a small distribution, and then when looking at the quadratures for the mechanics and the light field, or say for the two light fields actually, when one uses high powers, then one actually gets this wide distribution, and that looks just like a hot light field coming out and a hot mirror that is read out. So at this point, one cannot see the entanglement. Entanglement would mean now that each point here is correlated with a specific point on the other side. And what you still see here is that the variances, or how the variances of x square plus p square, so essentially the size of this blob, how this is going up when the measurement strength is increased. And here this EPR parameter that I showed you before is calculated, and they actually could show that the light and the mirror, or the membrane actually are entangled. So I showed you this because this is unarguably a superposition state of a macroscopic object, right? And the stronger, I don't know what the limitation in the driving is, but the stronger one drives it, the higher gets the occupation. At some point, one runs into nonlinearities and so on. You cannot do it infinitely, but there's the superposition state, right? And actually, this value of 0.9 here is partially limited because they cannot perfectly read out the signal they get. So they have a detection efficiency of, I think, 0.2, and a small detection efficiency destroys the entanglement between the readout pulse and the driving pulse. Now, if they correct for this effect, then they would conclude that the entanglement between the mirror and the first light pulse would actually be giving an EPR parameter. Now this was kind of strong field down conversion, if you like. And more recently, in a system that I also showed you last time, a very similar scheme has been realized, but now with the mechanical oscillator, that is the mechanical oscillator in the ground state, just from cryogenic cooling, such that, as I said last time, we can do single photon excitations. And this is a collaboration with Delft and in Vienna. Ralf Liedinger and Sung Hong are on this project, and Simon Gröblacher and Markus Astenmeier are the PIs. The whole structures are provided by Simon's group. So the idea is again the same. You saw that before. I could now use this zero occupied mechanical oscillator, which is again the photonic crystal, And I use a blue pulse, but not to drive very strongly, but just to occupy with a single phonon. This still requires like on the order of 10,000 photons to do that. And this is when I go to the down conversion picture, pretty much the same as when people were using like what I did in my PhD actually. Also, when you use down conversion, not driving very strongly the crystal, but you drive it a little bit weakly, and then sometimes a pair of photons come out, and if you do it right, this pair of photons would be entangled. Only the difference in this photon case, you have this polarization entanglement that you can use. What one uses here is actually the fact, okay, a photon exists here and a photon exists here versus there's none here and none here. And that's, of course, something that is more difficult to detect and also something that you cannot nicely rotate if you think about it in a qubit, right? Because it's not a simple transformation to go from 0 to 0 plus 1 superposition. Okay, so the idea is this. Again, one creates this one phonon, and then one uses a red detuned pulse again to read out the single phonon on the system. And this is how the system looks like. I actually showed this before. It's exactly the same experiment. So there's the write pulse and the read pulse. They go into the circulator, into the structure. Out again, the photons that are scattered are always scattered onto cavity resonance, right? Remember, we come in with a detuned pulse, and then they are scattered onto cavity resonance. So they would be the same frequency for both detuned pulses. Then there's this filter, and this filter is actually causing, it's a super nice filter because it is able to separate the single photons from these strong pulses. At the same time, it, of course, introduces a huge amount of losses, which is a problem. And then one does a kind of Henbury-Brown twist experiment, and where one has a beam splitter here, and then there's the photon separated, and we look at the correlations between these two detectors. So I said all of this, and this is what comes out. So one always has a pair of blue pulse coming in and a red readout pulse. And then after a long waiting time, one again has a blue pulse and a red readout pulse. And the waiting time is so long that the system can again equilibrate to its far below 0, below 1 occultation. So this is a zoom into these two pulses, and one. The right pulse has the right number of photons inside, but the read pulse is just a bit stronger, and one reads out only the first part of that. That is clever for many reasons, but one of them is that then you can actually choose when you want to look at the readout in post-processing, because you do heat up your system with such a strong pulse. And the question is, as I said, there's a lot of losses here. The question really is, how would I now see a non-classical effect? Right? This EPR entanglement that we looked at before so was almost disguised from the detection losses, and here this would be totally disguised. So the idea was to do something else, like in the very early days of quantum optics towards violation of classicality. So based on a Cauchy-Schwarz inequality, one can look at the G2 functions of this. So essentially what one does is this G2AA would be the case where one finds a photon from the right pulse in both detectors. And then the G2BB corresponds to measurements of photon pairs correlations between the readout photons. And then one compares this to, this should set an upper bound on the correlations where one sees what one would actually expect, that a read pulse goes into one and a write pulse into the other. And so one can infer this classical bound from these measurements, and then one sees that for a certain pulse here, this would be violated. So this shows a non-classicality in this kind of system. And if one, as a cross-check, does it between this blue pulse and this red pulse, for example, then one finds a very low value because you don't expect any correlation. The x-axis is actually the good. Thanks. The x-axis is the difference in it's essentially time, but discretized to our pulse, right? This would be n equals 0, n equals 1, and so on. It's yes, in this analogy, what we would get is one blue detuned photon would give us one on cavity resonance photon and an excitation on the mirror. So in that picture, it kind of vanishes from the blue pulse and goes into the cavity resonance. That's the A dagger, and then into the phonon, that's the B dagger. So it's not really like in down conversion where as the process goes to a pair of optical photons, like the original ones essentially vanishes. But in this case, it just loses energy and goes into the cavity. So yes. That's classical pulses. Yeah. Once more, sorry, I didn't. Yes. Yes, that's meant to read out it's essentially the same as in the last protocol. But the read pulse is exactly doing the same as in the last protocol. It's doing the beam splitter interaction between the cavity mode and the phonons, such that we get an occupation on the cavity. Effectively, yes. And this is actually shown here. So when the delta t is getting larger, that would be the time between the pulses. Then one can see that the correlations go down. It's not only the natural decoherence of the system, it's also the heating that we introduce, that they introduce via the pulses. Because this is one of the two big issues in this system. These pulses strongly heat up the internal temperature of the resonator, and then this would eventually, after some time, heat up the motion of this mode that we actually look at. Yes. Actually, in both cases, one can see it as a storage of the phone, and actually for quite a bit, right? Here it would be stored for like on the order of less than a microsecond or so. Yeah. If one could control the heating, it would be a bit longer, and if one could then still decrease the dissipation. It's just then it would be still only gamma left. Must say that the mechanical quality of this is already quite high. It's pretty much pushing. So I won't go into this much. I mentioned it before already. There's a very low detection efficiency. One is limited in the photon swap probability, which you can essentially tune via the strength of the pulses because of the heating. And this is why the experiment is not as easy as it might look like in the first place, because the duty cycle with 1 millisecond gives rise to a coincidence rate of roughly 1 per 15 minutes. So we are sharing lab with these guys, and that means there's whole days where we can't work because of the with this repetition rate of so the count rate would be like there's a pulse sent in, and most of the time no photon comes out, but then after like a second or so a photon comes out. And this is that one could do all of this much faster if the duty cycle could be faster, and the duty cycle is limited by this yeah. And actually now they have much higher Q structures still, and the problem now is that you can now store the state longer, but what you cannot do is wait only a millisecond. So actually the duty cycle increased because the structure gets better. So one needs to find a good spot to work. Yes. Yeah. And where this whole thing is going to is, of course, not only the correlation between light and matter, but then one could think of a scheme where one does this in two crystals, and then the photons from them are overlapped, and we project the two mechanical modes into this entangled state of 0, 0 plus 1, 1 occupation. Which would, of course, be very nice, because then we have really, for the first time, two entangled massive objects. I mean, they are pretty light. They are on the order of picogram, I think, but still. That's right. Yes, yes, I totally agree. I think I don't know how far one can push that, but I think the way to go would be simply getting the efficiencies better and better, instead of trying to find a way to see it in the lossy system. I think one just needs to get it better, because also, would become more useful, right? If one would really have this almost on-demand creation. Okay, I'm actually, I was a bit uncareful, I must say. So it's exactly true, yeah. So what has been shown has been an effect of non-classicality, and one would, by the system, of course, assume that this would be entanglement, but one can't say it because we don't. Now, I have a few more minutes. So, coming back to the pulse scheme, I was saying that there's this strong classical pulse, and this is kind of an annoyance for what one would do in the system. But now Igor Pikovsky, who was working at the time very, very strongly together with Michael Renner, who was working on the pulsing, actually had an idea of how one could actually use that. And even more than on the other things, I must make a disclaimer here. I think it really fits well to the topic of the school, and that's why I want to say it. But then there's many things in what I'm going to show you now that I have very little knowledge about. And so please see this as I'm making you aware of that this proposal exists, and we can also discuss a bit. I have been discussing with the guys, but I'm clearly not an expert. Okay? So the idea kind of, I mean, the idea was first, but it's kind of motivated by when there's proposals that would say that quantum gravity modifies the commutation relation between x and p for a massive object. And that would, of course, be only at very high energy scales. or if you want at very, very, very small displacement, say I would do this kind of pulsed projection on an extremely tiny scale, then at some point I should run into this deviation from. So one doesn't expect to come into this regime with such a measure. But then at the same time, we have a very, very sensitive readout. So the idea is, can one in this range where we are actually able to operate, there would be still a tiny signature left. Are we able to detect this? And the idea that Igor had was one starts off somewhere in phase space with the mechanics, and then one comes with this light pulse, and one kicks, now the classical kick, okay? One kicks this mechanical object. And now, in the theoretical description, ideally, and that relates to a question that you had before also, one would like to make a kick in P, and then a kick in X in the other direction, and then a kick in P again, and then close a loop. And what one would get out of this, as one can calculate, is a phase on this light path, which would have been interacting 4 times with the system. That, by some Baker-Hausdorff-Campbell calculation, that would encode the commutation relation of the mechanics in the phase of the light path. So if we think in terms of something that we know we can do, right, waiting for a quarter period and then doing something in P, and then waiting for another quarter period, that would mean we kick the system, wait for a quarter period, kick the system, wait again 4 times, always with the same path because it needs to accumulate the phase. And then, normally one would classically expect that one is getting back with the path to the same phase, but then because of this enclosed loop here, one gets some kind of geometric phase that encodes the commutation relation of the mechanical oscillator. So this is something that one should be able to measure, and the guys looked at all the details of what one needs to do, and looked at some proposals in the literature on how this commutation relation would be quantified, and without going into any much details, one can come up with a list of parameters for the optomechanics that one would actually need in order to disprove any of these kind of models. And back here, it looks already quite difficult. One already takes the measure of changing the wavelengths just for this. But then for the first part here, this doesn't look very crazy. So there's finesse of 10 to the 5, mass of 10 to the minus 11. So you could not use this photonic crystal type of thing for it, but like a normal mechanical resonator, frequency of 10 to the 5 hertz. That's all not too far-fetched. So what in my eyes this is mainly doing, it's showing that one really needs to think in this direction, because there might be really something out there in this type of table of experiments one can find. At this point, one cannot really meet these conditions, but it's, as I said, it's actually fairly feasible. And for the very last part of this lecture, I come to something that Hendrik already mentioned today, and I also will only briefly talk about it. I said many times throughout the lecture when talking about the nanoparticles that what we want to do in the end is, in the same way as Hendrik described it, some kind of matter wave interferometry with this. And we were on this always working together with Oriol, whom we had already in the beginning, who made one of the early nanoparticle proposals. So how should an experiment look like? We thought at the time, how should an experiment look like where one does such a matter wave interference part? I just had this as a slide. I don't need to mention anything about matter wave interference anymore after this morning's talk. And so let me just quickly show you how we would like to have that. This, what happened now after the particle fell and the wave function was expanding and it fell into a cavity, what was happening was that this pulse is measuring the state of the system, doing a projective measurement onto this cat state. And that's actually the only thing where it needs explanation, I guess. So instead of using real grating, really in the sense of made out of material or of light, here this idea relied on an optomechanical effect. And it actually brings together many of the things that I've been talking about. So if we have this cavity and we have this intensity distribution here like this, what I said is that we want this linear coupling. And then we get the omega over the x readout of our position of the particle, and that would project our, in this picture, it would just do a projection of our initial distribution on some point. It doesn't help a lot. But now if one could do a similar thing with a particle that is essentially interacting here at the intensity maximum, what we get is when the wave function is spread widely, we read the phase out of the cavity, we read some phase, and this phase depends on the omega. It's going with this to the square, and x square, where x is the displacement from this intensity maximum. And this means now that this phase carries information about how far the particle is away from the intensity maximum, but it does not carry information about the site where the particle is. So I can in principle not know where the particle would be found, and this is why I get a projection onto this kind of state. That means that I don't have a set slit size from the beginning. It means that I would probabilistically all of the times find a different size of the slit. But still, if one continues, then one gets an interference pattern that one would have to read out. In this proposal, it was again by a cavity. Whether this is the most clever way is the question, but so one would need, for a set of parameters that Oriol actually calculated and simulated, one would need a precision of 10 nanometer, which is not a big problem, right? The other things are a bigger problem. So why I like this? I mean, we were always very well aware that when it comes to this kind of things, the matter wave interferometry people like Hendrik or Markus Arndt or so have been thinking a lot about how you would actually do such matter wave interferometry. But then, so it was pretty clear that there's many routes and that this is maybe the way or maybe not the way to go. But then what was puzzling me all the time is when the particle gets so big, right? The particle in this case, and there's other reasons why that would be challenging, as you heard this morning. When the particle is so big, how even if you use a grating of light, right? It's just big. How would you actually? The superposition is smaller than the size of the particle actually. So how would you make a grating for that? And without decohering. And this is one way to do it. This is one way. We don't do a grating, we just do this projective measure. And one can then either post-select on the slit width and look at an interference pattern that comes out for the measurements with a certain slit width that dramatically would increase the number of measurements one needs, so that's maybe not the right way to go. Or one does like this optical detection of the the particle, and then one just recalculates, right? What we know from basic quantum physics essentially is that when the slit width gets narrower, the fringes get wider, and vice versa. We know how the scaling is. From the measurement outcome of the space measurement, we in principle know what we would expect, and then we can, in post-processing, kind of show that there is an interference. So I said the parameters are a bit hard. So okay, 40 nanometer spheres, okay, sideband cooling to 0.1 phonon. I hope we can do it. Point, but it's hard for such a small particle actually. This projective measurement is using almost done. Is using a cavity that one would need to have still very clever ideas on how to improve it, because the interaction is going here quadratic and it's really weak. So it's 2 micrometer long and a finesse of 130,000. So the finesse is fine, but 2 micrometer. It's really hard. And then, okay, the rest is all okay on this slide. One also has to think about the usual suspects, collision with gases, scattering, and so on. And in this old proposal, this is something that has improved, I think, in Orio's proposals meanwhile a bit. The pressure is still extremely low. And I personally think that it doesn't make sense at this point to think of pressure anymore, because maybe you can later comment, but because either it's kicked and decoheres or it's not kicked, independent of how many other parts. As soon as I know if it's kicked, then I would be fine. Yeah, exactly. And then one problem that one has in these spheres is that they internally heat up, so one would actually have a cryogenic environment. And this is just to mention, without going into details, for all kind of boundaries that one can calculate for limitations on the setup. He found that one can actually test for some CSL models, but I don't know details about it. As I said, after last week, you probably know more about it. I don't have a last slide, sorry. So that's it.